Hello, welcome back. We're going to hop right into lab number 4 on oscillation. So to begin, we'll get into the introduction for the purpose and findings. So the purpose of the lab was to observe the motion of a mass oscillating vertically on a spring. And to do this, we track the motion of a spring attached to a fixed point. And you can see that over on the right with the tracking data. And the initial findings that we had were that the model and the experiment were pretty similar to each other in both the x and the y direction. And then the change in total energy is 0. So to get into the other part of the introduction, the key concepts, we used Newton's second law, including net force on an object, F net equals change in P over change in T, the velocity update formula, VF equals VI, F net over M times change in time, and the position update formula, RF equals RI times RF times change in time. And then we also use the energy principle, which is the change in the energy of the system is equal to the W surroundings plus Q, and the system was the mass, the spring, and the earth, and the surroundings were none. And then we'll hop into the model. So for the first part of the model, this is the energy changes, and we can see the change in energy versus change in time, and you can see the change in kinetic energy, the change in the gravitational potential energy, the change in the spring potential energy, and the change in total energy. And the key over on the side to see which color is which. And then we'll get into the second model, which is the comparison of the model versus the experiment. So in the blue, you can see the oscillation for the model, and that one is more consistent than that of the experiment. And over on the left, this is a comparison of the model versus experiment in the x direction. And then over on the right, this is a comparison of model versus experiment in the y direction. And a little bit more about the experiment. The initial conditions were that the time was at 0 seconds, the initial velocity was 0 meters per second, and the initial position was negative 0.519, negative 0.619, and 0. Gravity, 9.8 meters per second. The mass of our ball was 0.402 kilograms. The spring constant for the spring we're using was 6.83, and the relaxed length of the spring was 0.123. And then we'll get into the code for the oscillation model. So the initial conditions, you can see the code over on the left, and then over on the right is the constants and energy that I've outlined in the experimental slide above. And then the continuation of the model, you can see the calculation loop over on the left. So it's a while loop, and then we calculate the energy changes, and then specify energy changes for plotting, and then plot x position versus time, and then update time. And then to get into the discussion, the results were that we found that the change in total energy is equal to 0. And the similarities and differences, the model was pretty similar to the experimental data, as you could see with the blue and the red lines in the model in slide number 5. There was more variation in the x direction and less in the y direction for the experimental than the model, and the experimental had wider oscillations than that of the model. And then the errors were, at the end of my code running, I had an error saying that one of the variables, line 161, was not a number, but it should have been. But I still had the expected results, so I continued on with the data that I found. And then finally, to get into the conclusions for the what does it mean, for your model system, is the energy principle satisfied? And I said yes, because the sum of the change in kinetic energy, change in potential gravitational energy, and change in spring potential energy were equal to 0, the total energy, which was that orange line in slide number 4. And then the second what-if question was, using the data you obtained in Tracker, make 2 separate estimates of oscillation periods by estimating the period of oscillation from the x position data and by estimating the period of oscillation from the y position data. So to do this, I found the time between the 2 peaks because that's the time to complete one oscillation. So for the average oscillation in the x direction was 4.653 divided by 3, which was 1.551, and the average oscillation in the y direction was 4.274 divided by 3, which is 1.424. And the difference between those was just 0.126 seconds. So it was pretty similar, but the differences that were there could have been caused by drag forces or an incorrect tracking of the center of mass because the camera wasn't of the greatest quality, so it was difficult to pinpoint where the center of mass was. And yeah, that's all. Thank you.